And hey, how are you guys doing? It feels like it's been a long time since we've talked math together. It's really only been a couple of weeks, but with everything that's happened, it feels like it's been a much greater time than that. We are going to get into our next unit, which is going to work with exponentials and logarithms. We are not going to really worry about assessing over our rational functions that we were working on right when we got called into this long break away from each other. So we're just going to pick up with the new material, kind of keep moving forward. And the goal is to have you working on the material, engaging with the material, learning as much as you can. And this is really just for the sake of learning. So as you look at this, we're going to try to keep it as close to our normal classes as possible, with the big exception being obviously that you can raise your hand and ask a question in the middle of a lesson. We will still be available. We'll have office hours, we'll have Google Hangouts, and different things. So just check the websites, check the Schoology site for information regarding those. But really, we want to continue in a manner very similar to what we established in class. So you're going to see on the Schoology site, you're going to see blank notes, you're going to see the filled in notes. You're going to obviously have the videos that you're listening to right now with everything that we have. And we really want you to take notes. We want you to try to do the problems on your own. There's going to be a lot of let me show you how to do some, then setting you off to work on your own, to check your work either through the video or the fully worked lesson notes. All right, so the expectations is that it's really going to function a lot like class in regards to what we want you to do and how you engage in the process. The only major difference will be then how do you get your questions answered when you have some. All right, and that should be either through email, through the Google Hangout, office hours, those kinds of things. So, as far as note taking goes, if you have access to a printer, great, print off the blank sheets, blank notes, and take your notes on them. If you don't, find some paper. It's loose leaf paper, whether it's lined, whether it's blank, but find something to where you can write the information down, and then hopefully keep it all organized in a binder if you still have your binder, or somewhere at your house. That way, when we do come back together, we will have a way of kind of gathering your things and having it all there with you. So, that being said, it is time for some math, my friends. All right, so when we look at the notes for today, all right, there is an opener there. And so, what I would really like you to do is try to figure out that problem. All right, so figure out how many wolves there would be at the end of 2 years, 5 years, and then see if you can write an equation that would model the growth of that wolf pack. And then this is kind of where that you do and then come back. All right, so go ahead and pause the video, attempt that problem, and then turn it back on. Let's see how you did. All right, so hopefully you found a way to figure this problem out. Now I'm going to flip over to the work that I did here. And now I think probably what some of you might have done is just did a table of values, right? And so that's kind of what I did over here off to the side, right? So we know at t equals 0, the population was 6. And if I'm going to increase by 50%, right, then I can take my initial population and divide that in half and then add that on. So half of 6 would be 3, so I can add that on. And then half of 9 is 4.5, I can add that on. And then all the way to where I get down here to where I get to 45.563. Now, the issue is that we're dealing with population, right? So hopefully we're not going to have 13 and a half wolves, right? That's not a very good situation, particularly for the half of the wolf, all right, that's left there. So it's a model, right? It's not exact, right? So we know we're either going to have 13 wolves or 14 wolves, all right? But it gives us a feel for that. Now, what you might remember is way back in Algebra 1, we talked about some exponential growth models, and we talked about something that looks a lot like what I wrote here, where the constant in front of the exponential is your initial value. And then what we talked about is that we have a number inside here that's being raised to a power, and this is our growth right here, or our decay factor, depending on whether we're going up or down. And so 50%, all right, is really equivalent to 0.5. So what you will see is if you do this equation, all right, you get the same values that we get here. And that's really the point of the lesson, is that we don't necessarily want to have to go through a table of values every time, right? We want to be able to kind of create that model and use that model to predict for any point in time. So let's flip back over, or at least I'm going to flip back over, you might still be there, to our notes here. And the good news is that the models for both exponential growth and exponential decay, both really look the same. The only thing that changes, all right, and so they both look like y equals, and then a times b to the x. All right, and our exponential decay looks very similar. It's just y equals a times b to the x. All right, and in both of our models, a is our original amount, all right, or our initial amount, whatever we start with, right? And you can see so that's our initial amount, whatever we start with. And same in both cases. So how do we know if it's growth or decay? We have to look at our exponential. If b is greater than 1, it's exponential growth, right? Now, when we think about exponential decay, we sometimes just say that b is less than 1, but really there's an underlying assumption here is that our base is always positive. All right, so when we're talking about exponentials, that was one of the things we defined it as, is that base always has to be positive. Otherwise, we don't get a continuous function. All right, we'd have some jumps and some gaps in that function. All right. Now, so the one thing that we have to make sure is that, like in the last problem, we were talking about increasing by 50%. So whenever we're working with this, right, it's going to be, all right, 1 plus our percentage. And that's how we get a number greater than 1, right? And then here it's going to be 1 minus that percentage, right? Now, I'm going to put this in parentheses here, is that we also have to just remember that we have to convert that percentage to a decimal, right? Okay, and so just make sure that before we do anything else, we just convert. All right, and my writing is almost as sloppy on this as it is in the classroom, so I apologize for that. All right, convert it to a decimal. And that's really all you have to do, all right, to get your exponential growth or your exponential decay model. So let's just jump into problem 1 here. So we have an initial population of Nerdville, where I am a resident half of the year, of 12,456. It says the population is declining at a rate, all right, of 3.85%. So now we know we're going to be in this exponential decay model because we are declining, right? So we're looking for those key words there each year. So we want to write an equation that models the population, and then we want to use that model to predict the population in 10 years. So the first thing that we want to do, right, is that we have 3.85, right, percent. All right, and so we have to convert that to a decimal. And then what we can do to do that is we just move the decimal places 2 positions to the left. So 0.0385, right? And that's our number here, right? Now, since it's decay, when we set up our function here, so our population, all right, is equal to, and then we have our initial amount, so 1, 2, 4, 5, 6, right? And then we want to do 1 minus that percentage as a decimal. So it'd be 1 minus 0.038. Oop. Take that out of there. I meant to skip the 8 there. Oop. Get it out of there. All right. Get back here. Make sure I get back to the right pen. And then 0.385. All right. And then to t, right? And so if we just clean that up, all right, we still have our initial value out here. So 1, 2, 4, 5, 6. And then that decimal would be 0.9615 to the t. And there's our model. So if we want to predict what the population is in 10 years, all we have to do is put in 10 for t up there. All right, so 1, 2, 4, 5, 6, and then we have 0.9615. Whoops, that does not look like a 5, looks like an 8. All right. Let's get back here. All right. Make sure the blue's on the right size here. And we just want to put that, raise that number to the 10th power. Now the good news is, all right, this is really just a calculator problem, right? And if you have your calculator, use it. I know we have a link in some of the intro materials for the free software like I'm using here from TI that you guys can download. So whatever you have access, just please use that, whether it's your phone, whether it's the download, whether it's your calculator. Then all we want to do is just type it in, just like it looks. And then remember, this caret key here is your power key. and then we want to put that to the power of 10. And so we can see that the population in Nerdville sadly has declined to about, maybe, stop writing, 8, 4, 1, 1. And I'm just going to round down here because once again, we're talking about a population, right? So we know it's going to be a whole number. All right, so here's what I'd like you to do is I'd like you to give number 2 a shot. So once again, pause the video, give that a shot, turn it back on. All right, so let's see how you did with our elephant Marvolium. Not Decilium for some reason. All right, so let me click right here. Okay, so we have a decays at a rate of 6.23%, right? And so we know we're back into that decay model, so we should have a base less than 1, right? And so hopefully you converted 6.23, right, to your decimal, right? So you had 0.0623, and then 1 minus that gives me the number here. And then once again, you just plug in 3, and hopefully you got to 98.94 grams. All right, so let's go back and look at some growth models. All right, so we've done 1, we've done 2. And the good news is the growth models are really, it's all the same. It's just a matter of, all right, whether we're going to have a model that is greater than 1 with our base or less than 1. So in World War Z, our population is increasing by 27%. So we see increasing, that tells us growth. All right, we know that 27, all right, if we convert that to a decimal, is 0.27, correct? All right. We have an initial population of 123,567 zombies. Oh, where's Rick Grimes and Michonne when you need them? All right, with that many zombies running around. All right, so write an equation that models the growth of the zombie population. Well, our population model would be P equals, and we'd have to have that initial population of zombies, 1, 2, 3, 5, 6, 7. And then we want to take our decimal and we want to add it to 1. So 1.27, all right, to the T. All right. And so that's our population. All right. So when we look at World War Z here and our zombie growth here, and if we want to predict how many there are after 5 days, all we want to do now is once we have this model, all we want to do then is evaluate it, all right, when T is equal to 5. And then once again, that just becomes, all right, a calculator problem. So let's come over here, 1, 2, 3, 5, 6, 7, and then we have 1.27, all right, to the 5th power. And let's see how many zombies there are. Ooh, a whole lot of them. All right, so 3, 7, 1, 2, and once again, I'm just going to round down here. All right, so we don't have parts of zombies, although on the, whether you're watching World War Z or The Walking Dead, there's definitely parts of zombies just kind of laying around, chomping at the bit a little bit, hoping that you're going to walk by. So, and I need to catch up on that since I've got a little bit of free time now. So there you go. So here's what I'd like you to do. If you go to the next page of notes, there's one more example here that I would like you guys to work on your own. So once again, just go ahead and pause the video and give that problem a shot. All right, let's get back and see, all right, how many people Brad Pitt could save. All right, so once again, it's a growth problem here. So he's going to infect, all right, the zombie herd, which has an original population of 13, and we know it's growing at 32% each day, so that converts to 0.32. So our initial population, and then our exponential here would be 1.32 after 1 week. All right, now we have to make sure our units match, and this says per day, so 1 week would be 7 up here. Or if it's 32% each week, then we'd put a 1 up here. So just make sure you consider that. And what that tells us is that, all right, that we have 90 zombies, right? So infected after that first week. So there you go. All right, so now that's exponential growth and exponential decay. Now another big piece of exponential work is interest and growth continuously and both periodically. And so what I'm going to do now is I'm going to go ahead and just pause the video, and I'm going to write in some formulas here that you're going to need to use, but that way you don't have to sit here and watch me write those. So I'm just going to pause, write some formulas in, and I'll come right back. All right, and we're back. So if you need to pause the video now to kind of write those down, go ahead and do so. I'm going to go ahead and walk through them with you so you understand kind of all the bits and pieces here. But we have a compounding interest formula where we compound a finite amount of times, and that's the first one. And then we have a compounding continuously where it's always compounding your interest or whatever when you're working with money or some other things, but typically money. And that's the second one, which is affectionately referred to as the PERT formula. But in our first formula, we have A equals P, and that P is your initial amount. All right, so whatever you initially invest in something, whatever that amount is. And then parentheses, we have 1 plus, and then that's R divided by N, and then close parentheses. And then R is whatever interest rate you are working at. Now, N is the number of times compounded. So we could compound monthly, which would be 12 times a year. We could compound semi-annually, which would be twice a year, quarterly, weekly, daily. So N is the number of times that you compound your interest, which means you take whatever money you make and then you add it to your original amount, and then you keep doing that so that your original amount grows by whatever that amount is, that interest is over that given period of time. And then we have RT as the exponent. So whatever the rate is times the amount of time that you have invested it. Now, so when you look at the compounding continuously, what you see is P is the same P as in the first one. That means initial amount. R and T are the same thing. All right, so that's the rate and that's the time, just like we see here. But what happens is that we're compounding continuously. All right, and so we're doing it every moment, right? Instantaneously. All right, and so what we get is a special number E, which is approximately 2.7. And this is an irrational number, and it's kind of that same category as pi as far as those special numbers that we use in mathematics, and comes up a lot. All right, and this Euler's number, it's a very cool number, and you'll see some more applications of this the farther you move into mathematics. All right, so that's all the pieces. So let me show you kind of how this works right here with example 5. All right, so we want to invest $5,000. All right, so that's going to be our initial amount. Let me scroll up just a little bit here so I can see that formula. All right, so we know that P is going to be 5,000, right? So A equals, all right, so I have my initial amount, so 5,000. And then I'm open my parentheses, and then 1 plus, all right, and then it's compounded quarterly at 14.7%. So compounded quarterly means it's going to happen 4 times per year. So that means N is 4. And then our rate is 14.7% interest, which, whew, I don't know if anybody's ever going to get that. But man, that's a very good interest rate. Now, just like we did before, anytime we have an interest rate, right, as a percentage, we want to convert it to decimal when we put it into our formula. So when we see this R right here, we know it has to be a decimal. So if I move the decimal place back 2 slots, that would be a 0.147. And I'm going to divide by N, which we said was quarterly, so that would be 4. All right, so there's that guy. And then we have RT as our exponent. So that's the same rate that we just put inside, so 0.147. And then times our, all right, how long we are going to invest this. And it tells us it's for 3 years, so times 3. All right. Now, once again, what's nice about this is that now we can just take this equation. We don't really need to do much simplifying because we want to know how much interest we will gain, right? Or how much we have, how much our investment will be worth after 3 years. So we can just come right to our calculators and type it just like it looks. So 5,000. And then 1 plus, and then we're going to have that 0.147 divided by 4. All right, and we want to close parentheses, and then we want to raise our parenthesis. All right, raise it to power, and we have 0.147 times 3. And just make sure that that's all up in the exponent with whatever calculator you are using. And if I hit enter, this tells me what it's now worth. All right, so at that interest rate, all right, So what did all right, so 5,000 and where do I see 5,000 and all right, feel like I made a mistake somewhere because my notes don't match here, but let me see. All right, so let me pause the video here and just double check my calculator real quick. All right, and that is a correct calculation of my calculator. On my notes, I left off a decimal place, so I wanted to make sure everything was good. So you can see that that we make about $80, a little over $80 over that 3-year period by compounding quarterly. All right, so here's what I would like you guys to do is try example 6. So we're going to use the same information here, but instead of compounding quarterly, I want you to compound monthly, which means 12 times per year. All right, so pause the video, give example 6 a shot, and let's see how you did. All right, so once again, I have the work all ready for you right here. So let me scroll down here. So notice everything's the same, right? So 5,000, except for I think I did my exponent wrong here. So let me check this here. I don't know where I got the 12 from. Man, I'll tell you what. Sometimes I think what I did was I put the 12 instead of the 0.4147. So let me just double check this one again. I almost feel like we're right back into school, right, with me making these mistakes, right? So 0.147, all right, and then times 3. And I think that's going to change our answer here. All right, so let me just erase this guy here, and let's come over here to the calculator and see what we get. So 5,000 times 1 plus 0.147 divided by 12. All right, and then we want to raise that to the 0.147 times 3. All right, and hit enter, and okay, there you go. So 5,000 and, oops, let me get my pen back here. All right, so 5,000 and 26.91. All right, so there you go. So hopefully those numbers match what you have. All right, so now let's go back and look at compounding continuously. All right, so let me scroll down here. Now with this one, all right, E is our base, all right, and our exponent. And so we just need to know the initial amount, the rate, and the time. All right, so when I look at example 7 here, right, we have an $8,000 investment, right? So our amount would equal to 8,000. All right, and now the key phrase here is compounding continuously, which tells us we want the PERT formula. So that means we want E. And then our rate is 3.3%, so that's going to be 0.033, and then that's after 4 years. And all right, now we go back to our calculator. Now, some of you may or may not know where the E key is. We have an E key just like we have a pi key, and here's the pi key that some of you already know. Here's the E key, so I want to go second division there, and that gives me the E, and I'm going to raise that to, all right, I'm going to have that 0.033 times 4, which is equal to 1,280 or 9,128.87. So you can see over that 4-year mark, all right, we made about $1,100, $1,128. All right, so here's what I'd like you to do is try number 8 on your own. All right, let's see how you did. Now, once again, I have the work right here, so I'm going to flip right over here. So there's our initial investment. We had our 5.3% interest rate, so it'd be 0.053 as a decimal, and for 5 years. And then I put all that in, and then hopefully you got to 65171.55. So you can see that over that 5 years, you made a little over $15,000. All right, a little rough, but I apologize for some of my mistakes. Like I said, it feels like you're just right back in class with me. All right, so now, once again, that's all for today. So what we want you to do now is, all right, try the homework. Once again, you're going to see the blank homework. All right, print it off, write them down, do the problems, check it, all right, with the Fully Worked solutions, all right, and then we will catch you guys next time. So take care of yourselves, have some fun in between, and we'll talk to you soon.